and welcome to this virtual seminar. This is a joint work with Mario Salvetti, who is there in Pisa with some of you. And so in the first part of this talk, I will introduce reflection groups, Coxeter and Artin groups, and I will tell you what the K-pi1 conjecture is about. And then in the second part, I will give an overview of the techniques and of our work with Mario. So let's get started. A reflection group is a discrete group generated by orthogonal reflections in Rn. And to every reflection group, there is an associated object called a hyperplane arrangement, which is the collection of all hyperplanes that are the fixed set of one of the reflections of the group. Let's go already to two examples, which you can see here. On the left, you can see the line arrangement of a finite reflection group. This is a reflection group which is generated by three reflections with respect to the three lines that you can see. And the group is finite. In fact, it is the group of symmetries of a regular, an equilateral triangle. And it consists of the identity, three reflections, and two rotations. It has order 6. On the right, we have an infinite arrangement associated with an infinite reflection group. And I will call infinite reflection groups affine reflection groups for a reason that we're going to see later. So in this case, the group is generated by infinitely many reflections, one for each line that you can see in the picture. However, a finite number of reflections is enough to generate this group. In fact, if you take any chamber, that is any triangle in this picture, any connected component of the complement of the line arrangement, say for instance this one here, you can choose a chamber and take the reflections with respect to the three walls of this chamber. Those three reflections are actually enough to generate the entire group. So the group is infinite, but it is nevertheless finitely generated. Here is an example with some more details. The symmetric group sigma n is maybe the most famous example of a reflection group. In fact, it can be realized as the group generated by the reflections with respect to the hyperplanes xi equals xj in Rn. And so to see this, you can look at these reflections with respect to xi equals xj. And these reflections, what they do is that they exchange the ith and jth coordinate of the point. And so they basically act as a transposition ij. And the group generated by all these transpositions is the symmetric group which acts by permuting the coordinates in Rn. Actually, you can even realize the symmetric group with one dimension less, because all these hyperplanes share a common line. So you can realize the symmetric group sigma n as a reflection group in Rn-1, actually, which is what we see in the example in the second part of the slide. So the symmetric group sigma 3 can be realized as a reflection group in R2, and we recover the picture that we saw in the previous slide. So we have three reflections, which correspond to the three transpositions in sigma 3. And then we have the identity and two rotations, which correspond to the two 3 cycles in the symmetric group. Reflection groups are a particular instance of a larger class of interesting groups, which are called Coxeter groups. A Coxeter group is defined through its presentation. It is a group presented or generated by a finite set S of involutions. So there is the relation S square equals 1. And in addition to those relations, for every pair of generators, there can be a relation between the two generators, and the relation has this form here. So the alternate product of S and T of a certain length, MST, is equal to the alternate product which starts with the other generator. So you start with T instead of S, and then alternate. You can already look at the example down here, where this relation has the form ABA equals BAB, where A and B are the two generators. And I said that reflection groups are a particular instance of Coxeter groups. In fact, given a reflection group, you can always realize it as a Coxeter group. You can always find a presentation such as the one that we see on the top of the slide. And to do that, we follow a procedure which I already sketched in the very first slide. So you choose one of the chambers of the arrangement. For example, here we can choose the bottom chamber. We can choose among 6 different chambers in this example. And we choose as generators the reflections with respect to the walls of this chamber. In this case, I call these reflections A and B. And so these are reflections, so they are going to be involutions automatically. So the relations A square equals B square equals 1 is for sure satisfied. And then if we want to find the other relations, the strange ones, we have to look at the dihedral angle between every pair of hyperplanes corresponding to the generators, and that angle is going to tell us the length of the relation. So, for instance, an angle of pi over 3 corresponds to a length 3 relation over here, which is ABA equals BAB. Very well. Feel free to interrupt me if you have questions. Otherwise, I'm going on. And the third family of groups that we are interested in today is Artin groups. Artin groups can be defined in at least 2 different ways, which we are going to see right now. The first way is, again, through a presentation. You can take any Coxeter group with its Coxeter presentation that we have just seen, and you can remove the relations S square equals 1 for all generators S. So you don't force anymore the generators to be involutions. And you get, therefore, a presentation of this type here, where only the pairwise relations between the generators are there. Okay, so for each Coxeter group, we have an associated Artin groups. Let's immediately see the example corresponding to the symmetric group sigma 3, which is a very simple example of a Coxeter group. In this case, we drop the relations A square equals B square equals 1, and we only retain the so-called braid relation ABA equals BAB. And we are going to see why this group associated with sigma 3 is called the braid group on 3 strands. So braid groups, as we're going to see, are a particular case of Artin groups. This is going to be our main example throughout this talk, this braid group, but you should also know that there are many more examples of Artin groups which are also interesting. For example, finitely generated free groups are a particular case of Artin groups. They arise if there is no relation between the generators. So conventionally, we say that the length of all relations is infinite. This basically says that there are no such relations. On the opposite side, we have free abelian groups where all the relations have the minimal possible length, which is 2, and the corresponding relations are commuting relations, like ST equals TS. And in between, we have the rich and interesting class of right-angle Artin groups, where basically we select some pair of generators, and those pairs are going to commute, and there are no relations among the other pairs of generators. Very well. And as I mentioned, there is a second way to construct Artin groups, which is equivalent to the previous one. I'm going to tell you this second construction in the special case where we start from a reflection group. So not any Coxeter group, but a reflection group which acts in Rn. But we can actually do this for any Coxeter group. It's just going to be a bit simpler for today. Okay, so if you have your reflection group W, you can look at this configuration space YW, which is obtained by looking at the action on Rn and looking then at the complexification of this action. So basically, instead of Rn, we now have C to the n, and we remove all the complexified hyperplanes in the arrangement. And then we take the quotient by the reflection group W. Okay, and a theorem, which is more than 50 years, no, a bit, yeah, something like 50 years old, says that the fundamental group of this topological space is going to be the Artin group associated with W. Now, this space might seem strange and scary, so let's look at our favorite example down here, which is hopefully going to give some insight in this construction. In the case of sigma 3, our configuration space, how is it constructed? We have to look at the points in C3, which are basically triples of complex numbers. We have to remove the complexified hyperplanes. So the hyperplanes have equations xi equals xj in this case. So the complexified hyperplanes are going to have the same exact equations. They just are now over the complex numbers instead of the reals, but nothing really changes. So basically, to go to the complement, we need to ensure that all these hyperplanes are avoided, which means that these three complex numbers should be pairwise distinct. And finally, we take the quotient by the symmetric group, sigma 3, which acts by permuting these three complex numbers. And if you think about this, this is basically the space of configurations of 3 points in C, of 3 complex numbers in C. So as a topological space, you can look in the bottom right, a configuration corresponds to choosing 3 points in C, and you don't care about the order of these points. So since there is a quotient by the symmetric group, those 3 points are undistinguishable for our purposes. So only they as a set are of interest to us. Okay, but we have to take one further step. We should look now at the fundamental group of this topological space. And loops in this space, in this configuration space, can be visualized as in the picture here. So basically, we should take we should take any starting configuration of 3 points and evolve it with the time that goes from 0 to 1. So these 3 points are going to move in C, and they're going to land when t equals 1 in the same 3 positions, but possibly being exchanged with each other, because we don't care about the ordering of those points. And what we end up with is a so-called braid. So we get a nice picture like this one. And at each point in time, at each moment in time, the 3 points should not intersect. They should never, they should never coincide, because the loop always has to stay in the complement of the arrangement. So these 3 strands are never going to collide with each other. And we have basically a kind of instance of a knot with some additional structure. Okay, and you can actually do the same for the symmetric group sigma n. There's nothing special about sigma 3, and you get the so-called braid groups on n strands. Very well. Now, Artin groups have been studied for more than 50 years now, but properties about general properties about Artin groups are actually quite difficult to prove. And in fact, there are very few theorems that work for a general Artin group. There are many results about families of Artin groups, but not much in general. In particular, here are perhaps the 4 most important open problems about Artin groups. We don't know if Artin groups are torsion-free, which is perhaps a bit surprising, because if you think about the presentation of Artin groups, there is no relation that should introduce torsion. So it is really expected that Artin groups are indeed torsion-free, but that's difficult to prove in general. We are not sure about what the center is. The conjecture is that it is trivial in most cases, but we don't know that. And the third point is that we don't know how to solve the word problem, which means that there is no, we don't know any algorithm to check if a product of generators is the identity or not, which is quite unfortunate, because like, if you want to do any basic computation, you really need at least to be able to distinguish 2 elements. That would be like the most basic thing that you want. So algorithmically, Artin groups are fairly difficult to understand. Finally, the problem that we care about today is called the K-pi1 conjecture. which goes back to the 60s. So it is a fairly old problem. And it says that the configuration space YW, which we have constructed in the previous slide, is actually a classifying space for the Artin group GW. Now, the red box reminds you of what this means. It means that the configuration space YW should have as its fundamental group the Artin group GW. This is the first requirement, and this is well known. So it is one of the two ways that I use to define Artin groups to you. So this is well known, and the difficult part is what follows: is to prove that the higher homotopy groups of YW are trivial, which is equivalent under some mild hypothesis to the universal cover being contractible. And I should stress that this conjecture is quite useful because the classifying space of a group is unique up to homotopy equivalence, and it carries a lot of interesting information about the corresponding group. For example, if you know how to construct in a simple way a classifying space, then you probably can also easily compute the homology of the group. And for our purposes here, one reason why this conjecture is interesting is that it actually implies the first point here. It implies that Artin groups are torsion-free. And this is because the configuration space YW is finite dimensional. So its homology is finite dimensional. It's like it vanishes after a certain point. And it is a classical result in group theory that this implies that there should be no torsion in the group. So this is like a topological statement, which, however, has non-trivial consequences, even if we just care about the algebra of our Artin groups. And in fact, as far as I know, this is more or less like the main way that one thinks that one can maybe find to show that Artin groups are torsion-free. Like this seems to be the most promising way to do that. What's the status of these problems? They are some of them are solved for some families of Artin groups. In particular, I state here some of the results. All four problems have been solved a long time ago for the so-called spherical Artin groups. Spherical Artin groups are those that finite Coxeter groups, which is the same as finite reflection groups. Okay, so when the Coxeter group W is finite, then somehow things are easier to understand. And in these classical papers in the beginning of the 70s, it was proved that all these four problems were solved. And in particular, I should mention Deligne in 1972 proved the K-pi1 conjecture for arbitrary spherical Artin groups. And the next family of Artin groups which we are interested in is affine Artin groups. So these are the groups that come from affine Coxeter groups, which is the same as affine reflection groups. So together, spherical and affine basically cover all the case of reflection groups, which are the groups, the Coxeter groups that are a bit more simple to think about. The first three problems for affine Artin groups have been solved very, very recently by McCammon and Salway, whereas the fourth problem, the K-pi-1 conjecture, has been solved for some particular families of affine Artin groups by Okonek and a bit more recently by Filippo Callegaro, Davide Moroni, and Mario Salvetti. Some of them are here today in this virtual room. And our result with Mario from last summer is a proof of the K-pi-1 conjecture for all affine Artin groups, regardless of which family they belong to. Okay, so this kind of ends the introductory part. Could be a good moment to ask questions if you have. And otherwise, I'm going to give you an overview of the techniques which can be used to solve this problem. And especially, I will start talking about the case of spherical Artin groups, because that is like a basic case which we should understand first. And then I'm going to give a very quick overview of how our proof works. Okay, seems that everything is clear. So yeah, so let's go on. So as I said, the best is to understand why the K-pi-1 conjecture is somehow easier to solve for spherical Artin groups. So for groups that come from finite Coxeter groups. And there are many ways to look at this story, to look at the proof by Deligne, and I'm going to tell you one of them today. And this approach, this point of view, passes through another way to construct spherical Artin groups, which is as interval groups. So the construction goes like this. You take any group G with a generating set and a special element small g in the group capital G. Okay, you can already think as the group capital G to be a finite Coxeter group, which is the case we are interested in the example below. Okay, so you have this group. Now you look at the interval between the identity and your special element small g in the Cayley graph of the group capital G with respect to the generating set R. Okay, so the Cayley graph is the graph with one vertex for every element of the group, and then for every vertex you have outgoing edges, one for each generator, which brings you from the element where you are to the element times the generator corresponding to the edge. And the interval between the identity and your special element G basically means that you look at all shortest paths from the identity to your special element, and you take that portion of the graph, just that. So all the edges and vertices that are part of some shortest path. Okay, and you define the interval group, which is associated with this interval between the identity and the special element G, You define it as the group generated by the same generating set, so just as a set, not as group elements. So we use basically the same letters, let's say, but we only keep some relations. We only in the presentation we only put the relations that you can explicitly see from the interval between the identity and small g. What does it mean for a relation to be visible? It means that if you have two different ways to go from one vertex to another one, then the product of the generators along the first path is going to be equal to the product of the generators in the second path. We are going to see this in the example here. Let me have some water. So the example that we are interested in is when you start from a finite Coxeter group. You use as the generating set the usual Coxeter generating set S, as before. And as the special element, you choose the longest element of the Coxeter group. Now, the longest element means the element with the which is longest as a product of generators, so whose minimal minimal way to write it as a product of generator is as big as possible. And longest elements only exist in finite Coxeter groups. So this is the crucial point where this construction fails for infinite Coxeter groups, because we don't have this special element here. But okay, let's stick with finite Coxeter groups now. Then what happens if we apply this construction of interval groups? So in our example, sigma 3, this would be the interval between the identity and the special element delta. In this case, the special element delta is ABA, which is also equal to BAB. So you can see that actually in this case, the interval actually covers all the elements of the group, and the special element delta is the only one of length 3. All the other elements have length smaller than 3. Okay, so how do we construct the corresponding interval group? So we look at our interval. Now we actually don't care at all about the vertices of the interval anymore. We only care about the labels of the edges, which are going to be the generators of both our old group G and of our new group GG. And so the interval group is going to be generated by the same two generators, A and B. But now the only relation that we see from this picture, so again, ignore the gray group elements. We don't need them anymore. And just look at the red generators, the red labels of the edges. And you can see that there is one relation that you can see from this picture, which is there are two ways to go from the bottom to the top. And one way is ABA, and the other way is BAB. So this is going to be a relation, in fact, the only relation in this case for our interval group. And you can see that we again recover the braid group on 3 strands, which we have already seen. And this is true in general. If you do this with a spherical with a finite Coxeter group, you get the corresponding spherical Artin group. Very well. Now you might ask, why do this? I mean, we have already seen 2 ways to construct Artin groups, so why do we need another one? The reason is that this combinatorial way to look at things fits into general theory called Garside Theory, which is very nice. It was, in fact, developed over many years for the main purpose of understanding Artin groups, and then the theory got interesting by itself, regardless of this particular application. And the theory is interesting and rich. I'm just going to summarize a part of it, which is this theorem here. So this theorem says that in the setting as of the previous slide, so you construct an interval group starting from some interval in the starting group. So the theorem is if the interval satisfies some combinatorial properties, which I am going to talk about in a minute. Okay, so some combinatorial hypothesis on the interval, then the interval group that you build out of this interval is going to be a so-called Garside group, and it's going to have some very nice properties. For example, the group is going to have a normal form, which is very useful because, in particular, it solves the word problem. So one way to solve the word problem, so being able to distinguish elements, is to have a normal form for elements of the group. And a Garside structure gives you that, in particular. But the thing that we are most interested in today is the second part of this statement. It says that basically there is a nice combinatorial way to construct a classifying space for the Garside group that you have. This is especially useful if you think about proving the K-pi1 conjecture, because the classifying space of a group is unique up to homotopy equivalence. Now, if you have a nice way to construct a classifying space for a group, and you have your configuration space that you want to prove to be a classifying space, you only then need to prove that these 2 spaces are homotopy equivalent, which is more or less the approach we are going to take, basically. Now, what does this classifying space look like? You should take the order complex of the interval, okay, and you have to take the quotient by, roughly speaking, the labels that come from the labels of the edges of this interval. I think it's easier to look at the example directly. On the left, we have the same interval as the previous slide, the one that comes from the symmetric group sigma 3. By the way, this interval satisfies the combinatorial properties that we need to apply the theorem. On the right, we have the interval complex, which is a union of 2 tetrahedra. This is the one on the left, this is one on the right. They are glued by one edge. These 2 tetrahedra correspond to the 2 paths, to the 2 maximal chains that to go from bottom to top in the interval. Okay, so now the picture is the order complex. Now we have to take some quotient of it, and in particular, all the edges, one-dimensional edges of the order complex are naturally labeled by some product of generators. So you just have to take the product of labels of the edges that you go through. So each of these edges is going to be labeled, and we take the quotient. So we glue together edges that have the same labels. For example, we have one A here, then another A here, and a third one here. All these A edges are going to be glued together. Actually, also all the vertices are going to be glued together, because in some sense they have the same empty label. So the quotient complex has only one vertex, actually. And the quotient goes on to higher dimensional simplices. For example, this triangle on the bottom left has edges A, B, and AB. And a triangle with the same labels appears also here. Here you can see A, B, and AB. So these two triangles are going to be glued together in the quotient. Okay, and so this is good, because I mean, maybe it's not the very first thing that comes to your mind, but still it is a fairly simple construction. And most importantly, it gives you a very small classifying space, or I mean, a small classifying space. Because if you know a little bit of algebraic topology, you know that from any group you can construct a classifying space. The problem is that it's going to be huge in general. Like, there is a general construction which gives you a huge in this case, infinite, of course, classifying space. But here we have a construction that gives a very small classifying space, which is very useful. And finally, I should get back to the combinatorial hypothesis, balanced lattice. I will skip the balanced part. That's a technical thing that is always going to be satisfied in our examples, so we don't care much about it. On the other hand, the lattice property is much more crucial. Being a lattice means that for each pair of elements of your interval, there is one minimal upper bound and one maximal lower bound. For example, if you take the gray A here and the gray BA here, their minimal upper bound is delta, and their maximal lower bound is the identity 1. Okay, so this interval actually satisfies the lattice property. Okay, and so basically this theorem is one way to look at Deligne's, one way to to understand one point of view to look at Deligne's proof of the K-pi1 conjecture for spherical Artin groups, because you can do this construction for any finite Coxeter group, and everything works well. So the interval that you get satisfy these hypotheses, so you can realize your spherical Artin group as a Garside group, like here. You can construct a classifying space, like in this theorem here, and then you can prove that this classifying space is homotopy equivalent to the configuration space that you care about. Okay, so the theory is very nice, and the construction is very nice. The problem is that it completely fails to generalize to infinite Coxeter groups. So people started trying, and the reason for this, as I said, is that the special element delta, which you put here, does not exist for infinite Coxeter groups. So people started looking at other ways to realize Artin groups as Garside groups. And what came up was another, in some sense, dual way to do this Garside construction. So on the left, it is what we have already seen. So on the left, you can realize spherical Artin groups using, starting from a finite Coxeter group, using the usual generating set and the longest element as the special element. On the right, now the idea is, okay, let's use all reflections as the generating set of the Coxeter group, and as the special element, use a so-called Coxeter element. Here are the pictures. So in the case of the symmetric group sigma 3, we have the picture we already know everything about on the left. On the right is what happens if you do this dual construction. So the generating set is not only A and B, but now there is also the third reflection C, that I call C. You can choose any of the two Coxeter elements of sigma 3. Coxeter elements in this case are the two rotations. So for example, we can choose A times B. And this is the interval that you get. So it looks fairly different from the interval on the left. And in fact, the combinatorics of the two intervals are fairly different. They also have names. And the name of the interval on the right is non-crossing partition poset. And so what happens is that you can do this, you can try to do this construction here. And now a Coxeter element is always defined for any Coxeter group. So at least there is hope for generalization to arbitrary Coxeter groups. And what you can prove, at least for finite Coxeter groups, is that the interval that you construct in this way, which is called non-crossing partition poset, is in fact a lattice. So this means that at least for finite Coxeter groups, this construction actually gives a dual, like an alternative dual way to realize spherical Artin groups as Garside groups. And this theorem was proved not so long ago by Bessis, and then in a more principled way by Braid and Watt. So now the question is there hope to do this beyond finite Coxeter groups? Because, I mean, finite Coxeter groups and spherical Artin groups, we understand them fairly well. So it's not like we needed necessarily an alternative way to look at them. What we want is a way that generalizes better. And however, a couple of years ago, McCammond showed that if W is an affine Coxeter group, the poset, the dual poset that you get from this construction does not necessarily have the lattice property. In fact, McCammond gives an explicit characterization of when the lattice property is satisfied, when it is not, and most of affine Coxeter groups fail to have the lattice property. So it is in this setting that we started our work with Mario. And what we did was to look at these non-crossing partition posets in the affine case, which in general fail to be lattices. And but nevertheless, we looked at the space that you can construct in the Garside theorem. So Garside theorem tells you, okay, if you have a lattice, you can construct a classifying space using this construction. What we do is, okay, we take that space anyway, and we hope that the lattice property actually is not necessary. And in fact, our first step in the proof of the K-pi1 conjecture is to show that even if you drop the lattice property, which is absolutely essential, like if you don't have further knowledge about the interval, so it's not like a hypothesis that is not very important. It is like very crucial in the proof of Garside's theorem. But in this case, we managed. So if you look at the intervals associated with the affine Coxeter groups, we managed to prove that the space that you construct is a classifying space anyway, even when the lattice property is not satisfied. This is probably the most interesting and unexpected step in our proof, but it's not the only one. So actually we needed to do quite some extra work from here to prove the K-pi1 conjecture. The second step was so since we need now to relate the classifying space that we have with the configuration space YW, which we are interested in, we need to relate these two spaces. And one way to do that is to change one of the two, say the configuration space YW, and change it so that its structure, like combinatorially, resembles the structure of the classifying space that we have. And in particular, we construct a CW complex of the same homotopy type as YW, which is naturally a subcomplex of the classifying space KW. This is related to the well-known Salvetti complex of a Coxeter group, but it is different. So this new CW complex has a fairly different structure from the more like well-known Salvetti complex. And then what remained to do was to construct a deformation retraction from the classifying space KW onto the subcomplex, which is homotopy equivalent to the configuration space. And this deformation retraction by itself required some work, and it is interesting, in my opinion, because it relies on a lot of interesting combinatorics and geometry of affine Coxeter groups. In particular, one important step in this construction was to prove that the non-crossing partition posets in the affine case are EL shellable, this property over here. Shellability of finite non-crossing partition lattices was proved in 2007. So this particular piece of our proof is by itself like an interesting extension of a result that was known for finite Coxeter groups to the affine case. Okay, that's enough for the proof. Of course, a lot of details are there. You can look at them if you're interested. But I want to end with some future possible research directions. One nice thing about our proof is that it gives a lot of new questions that really want to be answered. So the first research direction that comes to mind is, of course, to generalize all this proof to arbitrary Coxeter groups. And the next family that we could look at is probably that of hyperbolic Coxeter groups. So this question by itself carries a lot of sub-questions, because you can look at our proof and try to see what carries on to the general case and what possibly doesn't. So we mostly don't know at this stage. However, there is one. So if I go quickly back to this diagram here, the only thing that we did for a general Coxeter group is this part over here. So this construction of a CW model, a dual CW model for the configuration space, we did that for any Coxeter group. But everything else is, our proof was very specific to the case of affine Coxeter groups. So we don't know how much and what can be generalized to other Coxeter groups. There are other interesting directions. For example, looking at complex reflection groups. This is a parallel story that I didn't talk about. A bit more than 10 years ago, Bessis proved the K-pi1 property for finite complex reflection groups. So what we talked about today was real reflection groups, but you can ask the same questions for complex reflection groups, which are a generalization of real reflection groups. So Bessis did it for finite complex reflection groups. Now, in our work, we did the jump from finite to affine real reflection groups. So one can ask if you can do the same jump in the complex case, jump from finite to affine complex reflection groups. The third direction was suggested to us by Pierre Deligne, and it asks if you can drop the hypothesis of coming from a reflection group, so taking a more general so-called simplicial arrangement of hyperplanes. And so in the finite case, Deligne actually proved the K-pi1 conjecture in this more general setting of simplicial arrangements, not just for finite reflection groups. So he rightfully asked if you can drop this hypothesis also in the affine case and do this for simplicial affine arrangements. That is all. Thank you for listening to me.